Hello guys, and welcome to my presentation on our system for collaborative assembly simulation and user performance analysis. Now nowadays we've seen an increased popularity of VR and also the integration of VR in industrial processes. And through this we see a need for comprehensive collaborative systems that support these larger workflows of industrial processes. Some examples for collaborative system might be robot-human collaboration or collaborative factory design and analysis. What we have focused on is another area, which is assemblies, where you have a larger process of assembly sequence design, workstation design, and then training and performing the assembly. This is a collaboration of multiple disciplines, and a great advantage of VR here is that we do not need physical prototypes, which means that we have a lot shorter feedback cycles and less investment into physical prototypes. The goals that we have set for our system were to create this comprehensive system where we can perform a collaborative assembly design, analysis, and training. We want to give users direct feedback via spatial and statistical tools for analysis and understanding of the assembly. And we want to do this in the same environment the assembly is performed in. In addition, we set out to evaluate the set of metrics that we chose for the training and assembly success, and want to kind of to compare how they are able to represent the user in the assembly, especially when they're learning the assembly. The system consists of three major parts. First, we have the assembly sequence design and workstation design in Unreal Engine, where you can directly in the game engine define the assembly order and the workstation. And you can simply press a button and try this out either in desktop or in VR mode. You can also do a design review through this. And this gives you a very quick feedback cycle directly in the engine, but you can also package it and share it with others to perform these things. In addition, you might want to compare different sessions that you perform. So the system allows you to save your assembly process and the captured data as a session. And you can use this then later in the analysis, where we offer a metric visualization and spatial visualization for users to better understand the assembly and maybe improve their training success, for example. And this also can feed back into the design quite quickly, since it's possible to do everything of this in the engine. For the assembly design and simulation, we build upon a previous work of ours, where users can directly design the assembly sequence in Unreal Engine. For this, we are using the scene graph or world outliner. You can see the little boxes here. These are tasks directly in the scene graph. You can also define the workstation here. And together with our industrial partner, we've defined three major components that we need to properly represent the assembly. So first, we have a slot. You can see this to the right here in orange, telling the user something has to go here. Then we have materials, which is the parts that are being assembled, here outlined in green, telling the user I have to be assembled next with this outline. And we have tools, here as an example, the screwdriver. We might not need a screwdriver for these modules here, but I wanted to give an example here. Users can perform the defined sequence in the defined order, and we have added some physically realistic hands and collisions so that users can kind of see whether tight fits are possible and have a realistic way of checking the accessibility. You can see here how the highlighting changes as soon as you grab something, and we try to have halfway realistic grabbing. It's not perfect yet, but we're getting there maybe. This also means that we don't have to rely on prototypes as much, on physical prototypes, because users can just try whether a screwdriver can fit into the assembly when you're performing it. For the collaboration aspects, we looked at mostly use cases where one person is performing the assembly and others can watch the performer, can see live statistics and maybe give feedback. For this, we have two major use cases that we're interested in, where we have a trainer-trainee scenario, where a trainer can either show multiple trainees a first iteration of how it's performed, or you have a trainer and a trainee in a one-on-one session who, where the trainer is watching and is giving feedback. In addition, you can also use this wonderfully for design reviews, when you're still designing the assembly, where typically within our industrial partner, you have one person that is presenting, is collecting information about the assembly, and then others are watching. And like I mentioned, we have a desktop and a VR mode. And you can see some of the avatars here. So we chose to have an upper body because this also allows us to have an avatar that kind of has head gestures as well. So you can move the head independently of the body because the body mostly follows the hands. And this allows you to have a short set of gestures that you can use in VR. It's an example here of a trainee who might be a bit unsure of how to assemble this. And you can also notice how the expressibility here without hearing anyone, right? You know what they're thinking approximately. And depending on the controllers you're using, as you've seen, you've also have some hand gestures that you can use with pointing and thumbs up. I've mentioned the sessions. So the idea of a session is capturing one performed assembly from start, ideally to finish. You can see the in-game UI to the right here. And per task, we capture user movement as time series. So position, velocity, acceleration, and the distance. And we have some aggregate timings where we've tried a few different ones next to the total time, of course. So for one thing, we have idle time, which is to say not doing any of the others. Then we have inserting and holding. So holding a material with the intent of inserting it somewhere. Then we have teleporting. So kind of the time you take to aim the teleport and the number of teleports and how long users are looking at the UI. Since we have a UI that tells you the name of the current task and where we are in the assembly. And if you don't look at that very often, you probably already know what you're doing. In addition, we have devised our own assembly precision metric, where we compute it only when the user is close to a target slot. So when the thing that has to be assembled is already close to the target, with the goal of measuring the familiarity with insertion itself and kind of factoring out all the other external issues. It's a composite metric, and it consists of angular rotation, so how much a user is rotating it, the needed time from entering into these 20 centimeters, the number of collisions, which can also tell you a bit of the familiarity when they're fidgeting around or when you have a tight spot and the user doesn't quite know yet how to insert it properly. And a decisive measure which kind of tries to describe the straightness of insertion. And it's a bit contrary to the needed time, for example, because if you need a lot of time, but you're moving very straight, you probably know where you're going, but you're trying to be very deliberate in maybe a tight space or something like that. For the analysis of these metrics, like I mentioned, there's two kinds of analysis here. We have a metrics-based analysis. You can see to the right an example in VR where you can look at the statistics of all tasks. And you can also compare to previous tasks, to previous sessions. Here's a live example. So this is the desktop view where you have these metrics that you can look at live. And the trainee who might be a bit unsure, two teleportations to reach the such a short distance, a lot of angular rotation. Yes, and for the spatial analysis, we also integrated a previous work of ours into this collaborative system, where we have a trajectory visualization that gives a very nice spatial overview of how users are moving in the virtual environment. This also allows users to nicely compare different sessions because you can simply see how users move in space. And combined with the heat map, it might also be a good tool for workstation design, especially if you want to control where users are moving while they're assembling the object at hand. In addition to the metrics that we capture, we wanted to perform a metric evaluation to kind of see how these metrics change over time when users are learning an assembly, to see which metrics are a good fit of gauging the assembly performance. Because I don't think there's the best way yet to kind of define how a user is performing in such an assembly. For this, we had 7 participants who performed 3 sessions, also 3 runs per participant, and we're performing our battery assembly example that you've seen throughout the talk already. Here in the back, you see our task panel showing the user where am I at in the task, in the session, and the materials to assemble here on this table. I'd like to go through a few of the results here. I know it's a bit, it might be a bit much, but I thought it might be interesting to see how these metrics evolve over time. When we look at the time-based statistics, we can see that the first run was always the slowest one, and then for the second and third run, there didn't change. There was not a lot of change. Sorry. we can see that users pretty much stopped looking at the UI, which is probably to say that the highlights that we give users were enough for them to learn the task and didn't have to look at the names to help them anymore. We've also seen that only relying on task duration might not be enough. So not only relying on the whole task duration, because some users had issues with the VR tracking and were outside of the safe space in VR. And this kind of changes some timings that might not really represent the familiarity of a user with the assembly. We can also see our needed time here is going down, which is the time that's captured only when the user is very close to the target. Although there is a large variance, I'm guessing this is because we have quite a fidgety task with small screws, where users had some problems of learning it. So this might have converged a bit better if we had a few more runs, but you have to keep evaluation time short, I think. When we look at the movement, we can also see a trend that is constantly improving here. Velocity and acceleration are behaving quite similarly. Also, when we look at teleportation, we see that on average, it was quite consistent, which also tells me that the initial 10 minutes of familiarization that users might have had, might have been enough here. And we can see different user behaviors as well with teleports. So one user had a lot of teleports, but took very short time to teleport here, for example. And when we look at our assembly precision metric, we can also see that it's constantly improving. So the composite metric is going up here, and the singular metrics that are composing this larger one here with summed angular rotation, movement decisiveness, needed time, and number of collisions is steadily improving. Although not as much as I would have hoped, I have to admit. So maybe we would have needed much more runs to see how it develops over a longer period of time. In addition, we let users evaluate their own performance kind of subjectively, and we've seen that that doesn't really correspond to the timing that we measured here. So if we wanted to compare this and wanted to use self-assessment as a kind of baseline, it's probably not a good idea to do that, because it's some users thought they were slower even though they took less time overall. And from my observations, I think it's mostly dependent on the performance of the last few tasks, which doesn't really represent the whole assembly. So we've seen that users are quite quick at learning the interaction and navigation and task order, which tells me that that highlighting is very valuable in VR and that they can learn this quite quickly. We've seen that VR issues with the room spacing were present. So this has to be factored in when you are deciding on which metric to use for assessing performance, I think. And something like redirected walking would be very valuable here, or just a room that is able to encompass the whole environment that you expect users to move in. For the future, we would like to improve the analysis process and find further fitting metrics to compare. We would like also to distinguish more strongly between the training and the design analysis. For example, in design analysis, you might want to have different ways of grabbing a tool so that you can try out the accessibility while you're doing the assembly. On the other hand, for training, you might want to use a fixed way of holding it to show users or trainees how to hold it properly when they're doing it in the real world as well. Then we would like to integrate safety and ergonomics aspects. Since we are in a virtual environment, we can't really harm ourselves when we performing the assembly. And I think those are great avenues to go for virtual reality. And finally, we would like to perform a more thorough evaluation of the collaborative aspects of our system, which we haven't been able to explore properly yet. So to conclude, we've created a comprehensive collaborative assembly design, simulation and training system where we represent all these steps in the process, and we leverage VR for fast and inexpensive evaluation and training. And we've evaluated the development of different metrics when users are learning and have compared them with each other. Thank you very much for your attention, and I'll gladly answer any questions.